Hello everyone, I'm Sneha Bharati and my topic is particle size analyzer. It's an analytical instrument and today I'm going to share some details about this instrument. So here comes the introduction part. So particle size analysis is a technical procedure to characterize the size distribution of particles in a powder or liquid sample. We use a laser beam to target particles in a liquid or air stream. The resulting scattering angle deflection tells us about the characteristic of the particle size. Yeah, angle deflection pattern. Then measurement can range from 40 nanometers to 2.5 millimeters. The carrier liquid which we can use, that can be water, organic solvent, or oil depending on the sample, and it is widely used in R&D and quality control in industries involved with nanotechnology, pharmaceuticals, cosmetics, food, electronic materials, sintering materials, lithium-ion battery electrodes, etc. Yeah, so this is LS1320XR particle size analyzer. It offers best-in-class particle size distribution data, and it enables high resolution measurements with an expanded dynamic range. Here we can see the measurement range is from 0.017 micron to 2000 microns. So also the XR particle size analyzer provides fast, accurate results and helps us streamline workflows to optimize efficiency. It's a good one. So now we'll see the different measurement techniques for particle size analysis, and these are laser diffraction, dynamic light scattering, induced grating, sieve analysis, and image analysis. There are many more techniques, but these are some of the standard ones. So laser diffraction. So it measures the angle and intensity of light scattered by particles when illuminated by a laser. The size range is from 0.01 to 3000 microns. Here given it's 10 nanometer to 3 millimeter. Yeah, that's the same. Also, it is widely used in industries like pharmaceuticals, chemicals, and food. And this particular technique is fast and it provides a broad size range. Now, the second one is dynamic light scattering. So, this measures fluctuations in the intensity of scattered light caused by particle motion in a liquid suspension. The movement relates to particle size. Now, the size range from few nanometers to about 6 micrometers, and this is ideal for nanoparticles and colloidal systems, and it has high sensitivity to small particles. This is suited for particles in suspension. Now, induced grating. So it identifies the size of even smaller particles, that is from 0.5 nanometers to 200 nanometers, in solutions by electrically aligning the particles and then measuring their diffusion. Then also it gets used in pharmaceuticals, chemical suspensions, and biotechnology industries. And next comes sieve analysis. So it is another conventional method often employed for larger particle sizes. Basically, it passes through a series of sieves with different mesh sizes, separating them into size fractions. Size range is typically from 45, typically till 45, from 45 micrometers to several millimeters. They are common in industries like construction, mining, and agriculture. It is simple, inexpensive, and does not require a complex equipment. Next one is image analysis. So it is gaining prominence, allowing direct visualization of the particles and providing detailed morphological data. It is also a measurement technique. Yeah. So particle size result interpretation. So particle size results are typically reported based on measurements taken using techniques like laser diffraction, dynamic light scattering, or sieving. The interpretation of particle size results depend on the context in which the particles are being studied, and each technique generates a different result. since each measures different physical properties of the sample. Here, first one is laser diffraction. Also, what is the need of interpretation of particle size? So yeah, like different fields such as suppose pharmaceuticals. So smaller particles there may dissolve faster, improving bioavailability, while larger particles may settle more slowly in suspensions. Then suppose in cosmetics industries, so the size there affects texture and skin absorption. And construction materials, so particle size impacts their properties like strength, mixing behavior, porosity, and all. So these are some of the applications. Basically, we need to interpret the particle size results. So laser diffraction. So in laser diffraction, on the x-axis there will be particle size. Size of the particles is usually in microns, and that is it, and that is given taken as in the form of diameter. And on the y-axis there will be volume percentage. Yeah, volume percentage. So like the percent of the total sample volume contributed by particles for a given size range. Different types of the graph here we can see that is a single peak, but different types of graphs can be there. That can be single peak, multiple peaks, tail or broad distribution, like that. Here it is single peak, so as it is a single and sharp peak, so it indicates that the sample has a uniform or narrow size distribution, and like most particles are similar in size. If there would have been multiple peaks, then that indicates a polydispersed sample with different populations of particle sizes. For example, a bimodal distribution might indicate two dominant particle size ranges. And if there is suppose a long tail is there, suppose if on the left or on the right, then that suggests the presence of a wide range of particle size where the tail is long. And a wide flat curve indicates if there would have been a wide flat curve, so that indicates a broad size distribution. Now the next one is dynamic light scattering. It also assumes hard spherical shaped model. And on the x-axis, here the graph on the x-axis, there is diameter, which is particle size, and on the y-axis there will be intensity, volume, or number percentage. Here we can see it is the graph is given in the form of volume percentage. So volume distribution that converts the intensity data into volume-based size distribution, and that reflects in a better way the actual volume occupied by different particle sizes. Um, Here also there could have been sharp peak or multiple peaks, broad peak, polydispersity index and all. But as per this graph, we can see that it has multiple peaks. So in this case, so if that's the case, we can, if that's the case for multiple peaks, then the sample contains particles of significantly different sizes. That's it. And if there, and there, yeah, we can see that there's a sharp peak also. So the sharp peak suggests that the particles there are of uniform size with little variability. And if there would have been broad peak, so broad peak indicates a wide size distribution, often due to sample polydispersity. And this is volume based distribution, but in dynamic light scattering there are two more types also, like intensity based distribution and number based distribution. So if suppose intensity based distribution curve would have been here, then that distribution tend to over represent larger particles because light scattering is more sensitive to larger particles. Basically, intensity based distribution, they represent larger particles more. And if there would have been number-based distribution. Then that gives a clear view of how many particles fall into different size ranges, making them better suited for samples with a mixture of sizes. Now this is for image analysis, and it measures particle projection with no shape assumption. Like previously we have seen that the particle shape was spherical, but here we can see that the shape, they have taken like any type of shape. Here also on the x-axis there is particle size, which is diameter, particle diameter, and y-axis there could be number, volume, or area percentage. Yeah. Also, the curves, they show that could be monodisperse curve. Like if number-based distribution curve is there, then that could be monodisperse curve, which will have sharp peak, and polydisperse curve, which will have a broad or multiple peak, which shows wide range of particle sizes or multiple size populations. If multimodal distributions and several distinct peaks suggest the presence of different group of particles, with each of them with its own size range. If volume or area-based distribution curve, then they emphasize on larger particles basically. So in volume or area-based distribution, larger particles will dominate the curve. Even if larger particles are fewer in number, they will contribute significantly more to the total volume or area due to their larger size. For example, if there are few large particles and many small ones, the number-based curve might show a large peak at the smaller size range because they are large number, right? While the volume-based curve would have a peak in the larger size range due to the volume dominance of the larger particles, like that. So in particle size analysis, mean, median, and mode, they are essential statistical values used to describe the distribution of particle sizes in a sample. Each measure provides unique information about the central tendency or characteristics of the particle size distribution. So here mean. So mean, we all know that it's a calculated value similar to the concept of average, and mean gives an overall estimate of the average size of particles in the sample. And it is useful for characterizing samples where the particle sizes are relatively symmetrical or normally distributed. But it can mislead in a highly polydispersed system, as a few large particles can skew the mean toward larger sizes. This is a formula, volume mean diameter formula, which you can use. Median. So median actually provides a better representation of the central tendency when the particle size distribution is skewed. That is when there are more small or large particles. And also it's a robust measure that is less influenced by outliers or extremely large particles, unlike the mean. And the mode, so mode indicates the most common particle size present in the sample, which is important for processes where particles of a particular size dominate or are more influential. So it's a research paper, a comprehensive review of particle size analysis techniques. So in this research paper, they have just reviewed the application of particle size analysis, limitations, and the factors affecting particle size analysis. So we'll see them. So their objective is the dissolution rate and bioavailability of active pharmaceutical components are only two examples of how particle size and shape may impact these and other crucial physical qualities, manufacturing process abilities, and quality features. Yeah. Here we can see the application of particle size analysis. So the size reduction process is beneficial in facilitating the quick development of solutions in chemical substances as it effectively enhances the surface area of drugs. The increased surface area makes the extraction of active ingredients from animal glands and food vegetable pharmaceuticals easier, allowing solvents to readily permeate the tissues and aid fast extraction. The therapeutic efficacy of particular drugs may be enhanced by reducing particle size. The decrease in size is of significant importance when considering suspensions. The formation of a cake, which may provide challenges for redispersion, may occur when particle size is too tiny. Therefore, it is crucial to consider and choose an appropriate particle size. And the optimum particle size is of utmost importance when considering inhalers also. Tiny particles may be expelled from the bronchioles along with air without causing any noticeable impact, whereas much larger particles may fail to reach the alveoli and be absorbed into the bloodstream. So this is application of particle size analysis according to that research paper. Limitation is it is not suitable for all drugs containing volatile oils and must not be subjected to heavy grinding to prevent the loss of volatile oils. Due to the increase in surface area, oxidation and hydrolysis may occur when exposed to atmospheric conditions. Therefore, these drugs must be stored in a well-closed container and in a cool place. Factors affecting the size reduction we can see. So hardness is one of the factors. Surface property of the material is a significant characteristic. So it's conceivable for a substance to possess hardness. Nevertheless, if it also exhibits brittleness, reducing its size may not pose any significant challenges. Toughness. So in terms of practical importance, toughness trumps hardness since it is more challenging to decrease the size of a soft but robust material than a hard but fragile one. Liquefied gas treatment, nitrogen for example, might lessen the material's toughness. Abrasiveness, so it refers to the characteristics of hard materials, especially those derived from minerals, which might impose limitations on the equipment used for grinding purposes. This is because the material being ground can get contaminated with the worn out particles from the machinery owing to the high level of abrasiveness shown by the material. Softening temperature, so softening temperature of waxy substances may be attributed to the thermal energy produced during the grinding process. Yeah, softening temperature is also an important factor for size reduction. If this temperature will be more, then size reduction will be easier. Material structure. So material structure of minerals may exhibit lines of weakness similar in structure seen in vegetal medicines. Yeah. So a particle size analyzer is a key tool across many industries allowing precise control over the properties of materials. By selecting the right analyzer based on the sample type, particle size range, and application needs, we can obtain accurate, reproducible data that informs product development, quality control, and research. Thank you.